Okay, this is chapter 11 homework help. Problem 59 says we have an experimental train which is a mass of 2.5 times 10 to the 4 kilograms, powered across the track by a jet engine, produce a thrust of 5 times 10 to the 5th newtons over distance. So we want to find the work. Well, we have work equals force times distance, so we can easily use that formula, which we have the force that's making this train go forward, which is 5 times 10 to the 5th times 509 meters. That gives us the work about 200. Let's see, 254,500,000. So about 254 million, and that's joules energy for work. The change in kinetic energy, well, we actually know that's the same for part B because we know that work equals the change in kinetic energy. That's the work energy theorem. So we know that work equals change in kinetic energy, therefore we know that it's the same answer for part B. Part C, find the kinetic energy of the train if it starts from rest. If it starts from rest, then what that means is the kinetic energy final minus initial. We know that if it starts from rest, there is no initial, so the work equals the final kinetic energy, so we give the same exact answer for C. So the same answer is for A, B, and C. Part D then says the final speed of the train if there had been no friction. Well, we know that we have 1/2 mv squared for kinetic energy, and we know the mass of this thing is 2.5 times 10 to the 4th kilograms times the speed, but we know that this energy must equal this number, 254,500,000, because that's how much energy there was. So you can then solve this equation for V, and if we do that, we get don't forget the square here too. When you solve that for V, you should get 142.7, and that's meters per second since the units that we're in. So we would have to convert that to kilometers per hour if we wanted to, but that's the answer in meters per second. Okay, next question, 61 says we have a 15 kilogram cart moving at this speed on a level hallway. The constant force of 10 newtons acts on it, and its velocity becomes smaller. So the first question was the change in kinetic energy. Change in kinetic energy is kinetic energy final minus kinetic energy initial. So the kinetic energy final is 1/2 mv final squared minus the kinetic energy initial is 1/2 mv initial squared. So this is what we're solving. You can factor out a 1/2 m if you want. And so you just have, I don't know if that helps at all, but that's mathematically equivalent. So I can do 1/2 times the mass times the final velocity squared, which was 3.2, minus the initial velocity squared, which is 7.5. And then the mass of this thing was 15. So that's the numerical value that give me the answer for part A, which is negative 345.08, I guess, or 0.1 meters per second. I'm sorry, that's joules. I don't need this negative. Well, we're just talking about the amount of energy, so we'll use this as a scalar quantity. Okay, next question is part B. How much work was done on the cart? Well, we know the work equals the change in kinetic energy, so we know that the answer to this is still 345.08 joules for our work as well. Part C then, how far did the cart move while the force acted on it? Well, we know work equals force times distance. So if work equals force times distance, we know that's 345.1 joules. So we can plug in the force that they gave us, which was 10 newtons, and we can solve for the distance that it goes by dividing both sides by 10, and we get the distance equals 34.5 about meters. All right, the next problem says that we have a tennis player exerting an average force of 150 newtons on the ball. If the ball has a mass of 0.06 kilograms and it's in contact with the strings for 0.03 seconds, what is the kinetic energy of the ball as it leaves the racket? So we're looking for the kinetic energy, which we know is equal to 1/2 mv squared. So we have the mass, we just need the velocity, or we need the work. The other thing is we know that work equals change in kinetic energy. Work is force times distance, so there's probably different ways to do this, but I'm going to find the velocity of the thing final. And I'm going to do that by using the impulse momentum theorem. We had that impulse equal the change in momentum. That's the other formula we have. It gave us the force of 150 newtons. It gave us the time interval that it was in contact for. So I can set that equal to the mass times velocity final minus mass times velocity initial. And velocity initial is 0 because it says the ball starts from rest right here. So we can solve this. This is 150 times 0.03 equals the mass of 0.06 times, drops out to 0, times the final velocity. We could find the final velocity by dividing both sides by 0.06, which gives us a value of 75 meters per second. So now we can do the kinetic energy formula, 1/2 mv squared, to find what they wanted, which was the kinetic energy. The mass is 0.06, and it's 75 squared, which ends up giving us 168.8 joules. All right, next question says we have a car that has a mass of 2 times 10 to the third would be 2,000 kilograms. So the car is mass 2,000 kilograms. The velocity is 12 meters per second. And it hits the tree and comes to a rest, so we know the change in velocity, or the final velocity, is 0. And it says find the change in kinetic energy is kinetic energy final minus kinetic energy initial. So that would be 1/2 mass, which is 2,000, times final velocity squared, which is 0, so that just drops out. And the change in kinetic energy is just the initial, which is 1/2 mass 2,000 times initial velocity 12 squared. And that gives us 144,000. And that's joules. Part B, the amount of work done as a car crashes in the tree. We know work equals the change in kinetic energy. So once again, we know that work equals 144,000 joules. Part C then, find the size of the force that pushes in front of the car by 50 centimeters. Well, work equals force times distance. So we know that we can set this equal to 144,000. And we can find that force if the distance is 50 centimeters, that's 0.5 meters. So 0.5 times F equals 144,000. Divide that by 0.5, or multiply it by 2, and you get 288,000 for our force, and that's in newtons. Technically, these are negative because the force is acting against the direction of motion, so this force would be negative. So technically, that would be negative, but that's not something I'm going to be too concerned about right now. I'm going to mark you wrong for that on a test. All right, next question says a 20-kilogram rock's on the edge of a 100-meter cliff. As shown, what's the potential energy of the rock? That's potential energy equals mgh for gravitational potential. So the mass is 20, gravity is 9.8, and the height of this thing is 100 meters. So that gives us a value of 19,600, and that is in joules, because that's energy. That's part A. Part B, the rock falls from the cliff. What is the kinetic energy just before it strikes the ground? Well, we know that has to be the same answer because of conservation of energy. We know all the energy that was stored in this rock in terms of gravitational potential, when it reaches its reference line, so when it reaches its 0 height, all that energy that was in gravitational potential is now in a different form of energy, which is obviously kinetic energy because it's moving. So we know the kinetic energy right away because of conservation of energy has to be the same. And from there we can find the speed that it has right before it strikes the ground, because we know that kinetic energy equals 1/2 mv squared. So we know that 19,600 has to equal 1/2 times the mass of 20 kilograms times the velocity squared. So this is 19,600 equals 10 times velocity squared. Divide both sides by 10 and take the square root, and you get the velocity equals 140 meters per second. And I, for some reason, added a 0 back onto this one. I don't know why. And so I got the wrong answer. This should have been 44.3 meters per second. That's right. Okay, this next problem says a railroad car with a mass of 5 times 10 to the 7.5 kilograms collides with a stationary railroad car of equal mass. After the collision, the two cars lock together and move off at 4 meters per second, as shown. Before the collision, the first railroad car was moving at 8 meters per second. What was its momentum? So the first railroad car is just mass times velocity for momentum. So the mass is 5 times 10 to the 5th kilograms times the velocity of 8 gives us an answer for part A of, that'd be 4 million, so 4 times 10 to the 6th kilogram meters per second for momentum. And then part B, what's the total momentum of the two cars after the collision? After the collision, the total momentum must be the same because of conservation of momentum. So afterwards, we should have 4 times 10 to the 6th kilogram meters per second as the same momentum. What were the kinetic energies of the two cars before and after the collision? Before, the kinetic energies of the two cars, we had car 1 and car 2. Car 2 wasn't moving, right? So that's 0. But the kinetic energy before for car 1 was 1/2 mv squared. So it'd be 1/2 5 times 10 to the 5th times the velocity 8 squared, which gives us a value of 1.6 times 10 to the 7th, or 16 million. And that's joules for kinetic energy. So then after, the two lock together, so then they both have this kinetic energy of 1/2 mass 1 plus mass 2 times their speed. And I said afterwards they move off at 4, so it'll be 4 squared. So let's plug these in. The mass of both of them would just be 2 times the 5 times 10 to the 5th, because there's 2 of them, times the velocity of 4 squared. So that gives us an answer of 8 times 10 to the 6th, or 8 million, and that's joules. So that's important to compare these two, because what you notice is that the kinetic energy as they move off together is different from the kinetic energy before both of them added together. So obviously energy was not conserved here. Obviously some energy was given off in the form of heat or in the form of deformation of these train cars. But some of the energy was given off here. Conservation of energy does not work for this. So this was an inelastic collision. That's important, because conservation of momentum is always going to work here, as you see. But conservation of energy doesn't always work. Sometimes energy is given off during the collision. Okay, the next problem gives us a ball that's thrown straight down from a height of 2 meters. And it says it reaches the floor with the speed of 7.5 meters per second. What was the initial speed? So let's do conservation of energy. Let's do energy before equals energy after. So before we have kinetic energy because it's thrown with some speed plus potential energy, and afterwards it just hits the floor with only kinetic energy. So beforehand we have 1/2 mv squared, where we don't know that initial velocity, and it also has mgh for potential energy. And then we have 1/2 mv final squared. So let's plug this in. The ball has a mass of 10 grams, which is 0.01 kilograms. And it's got a velocity initial we don't know, plus a mass of 0.01 times 9.8. Whoops. 0.01 times 9.8 times a height of 2 meters equals 1/2 times the mass of 0.01 times the final velocity of 7.5 meters per second squared. So there's our equation that we're solving. We're solving for that variable right there. So we're going to have to subtract this to the other side, and we're going to have to divide by 1/2 times 0.01, and then take the square root. And that should give us the initial velocity of 4.13 about meters per second for the initial velocity. Okay, the last problem I had to do, because I'm running out of time a little bit on this video, but I know the energy before, energy is conserved, so I know all the energy before has to be equal to the energy at the bottom plus the work that's given off by friction. So that's why I wrote this equation. And then I just subtracted the energy after from both sides, so the work equals the difference in energy. Well, the difference in energy at the top, it's all potential, and at the bottom it's all kinetic. So I just plugged in mgh, and we'll have mv squared. Plugged in the numbers and solved, and that gave me an answer of 1,145.6 joules.